Yeah, so welcome everyone. It is my absolute pleasure to welcome Professor Yamila Miguel from Leiden Observatory and Esron, Netherlands. She's here to talk to us about peering inside giant exoplanets. So just to give a little bit of introduction to her career, so she started her bachelor's already in astronomy in Argentina at La Plata National University. And then she also did a PhD there. After that, she moved to Europe and has been there in Europe in different countries since 2011. First, she went to Heidelberg for the Max Planck postdoctoral fellowship. Afterwards, she was a CNES fellow for a couple of years. Then she moved to Leiden in 2018, where she started as an assistant professor. And now she is an associate professor. She also won a ERC consolidated grant in 2023. And she has been also a Dutch co-PI of Ariel mission. So it is again, a pleasure to welcome Yamila, and I will give the floor to her.
Thanks. Thank you, Kasu. Hello, everyone. So it's really nice for me to be here. I don't know why, but it's my first time in Leuven. Leuven here. I came to the city, but never to visit you. So it's my pleasure to be around. So today I will tell you a little bit about the work that we are doing in my team. So let me start there. So here is a picture of the people in my group. We are working with exoplanets, but also with planets in our solar system. So we work with Jupiter, Saturn, Uranus, Neptune, and exoplanets, both giant and rocky. And the idea is to characterize, to understand how planets form, to understand how they evolve, to understand more about their interiors and their atmospheres. So today, because of course I don't have time to talk about everything, I picked a topic and I decided to tell you about the work that we are doing on the giant planets. So a little bit on Jupiter and Saturn, and then how we use that to understand more about exoplanets. So first thing is why we are really interested in understanding exoplanets, and why giant planets in particular, why we care. And giant planets are really the first planets that form in a planetary system. They are born in the first millions of years, when there is still gas in the protoplanetary disk. And because of that, and also because of their evolution is quite different from the one of rocky planets that have differentiation processes and many things in the chemistry change in the interior, but giant planets do not have that. So their envelopes are mostly primordial. They still have the hydrogen and helium that they accreted from that. And that's why understanding more about their interiors and their atmospheres also help us to understand more about the process of planet formation. Now, that is really one of the reasons why I think it's interesting to study them. There are others, and here are just a few of my favorites, but there are more. The second one is that they are really very influential in the evolution and in the architecture of the final planetary systems, because they are so huge that they really dominate the entire dynamics of the system. So in our solar system, for example, Jupiter was really key to understand everything, like how the asteroids, the comets were moving around, where the Earth and the rocky planets were born. So really understanding more about their formation and their evolution will help us also to understand more about the dynamics and the final architectures of the systems. Another thing that is also more related to the topic of today is that they are natural laboratories. And in the sense that they have in their interiors very special conditions of temperatures and pressures, so very high pressures, high temperatures, but not as high as the interiors of stars, but they are very dense. So it's a very special regime that also pushes us to understand properties of materials like hydrogen, helium, metals at very special conditions. And that's why I think that they are a natural laboratory. We understood many things, as I will mention during the talk, particularly about hydrogen and helium, just because we are curious to know more about the giant planets. So that's also another of the motivations to study them. And the final two, One is that, in particular, if we think of exoplanets, the giant ones are the easier to characterize. We are, of course, trying to put all our efforts to also observe small planets, but they are much more difficult. Giant planets are much easier. With just one transit orbit of JWST, we get great information, as I will show you later. But also, we got recently huge and great data from our solar system giant planets as well. So we had 2 missions, the Cassini mission that went around Saturn and was there for 20 years and made great measurements of the planet, the rings, the atmosphere, the satellites, but also the Juno mission that is still there. It has been orbiting Jupiter since 2016. And I will show you just some of the results that we found with the Juno mission that was really key to understand more about, in particular, the interior, but also the atmosphere of Jupiter. Right. Now, the biggest questions when we are thinking on giant planets is, first, how is that they work? And in this sense, I'm referring to the inner workings, so which is the structure that they have. Which are the links between the interior structure and the atmosphere. So this is really one of the questions that we still don't know. We have some answers. I will show you what we know for the solar system giants, but these are still open questions for exoplanets. Also, as I mentioned before, we don't know how they form and evolve, and I think a key question here is also to understand more about the links to what we observe and what we can really say from those observations about the formation and evolution of the planets. So here, this refers not only, of course, to exoplanets, but all of these are also open questions for the giants in our solar system. So understanding more about this will also help us to know more about our own history. Now, the problem is very complex, because when we are observing a planet, the only thing that we see is the atmosphere. And the atmospheres are just a tiny, tiny, tiny percentage of the entire planet. So then, really, we need to understand more about what happens in the interiors of the planets, about what are the links with the atmosphere, how is the material transported from the interior outwards, how is that evolving with time, because all of that will, when we observe the atmosphere, all of that will be reflected there. So we need to go backwards, right? We need to see if there are really tracers of planet formation that we can see in the atmospheres. So that's why really I'm interested in the interiors of the planets. I also work with atmospheres, but today I will mostly focus on our knowledge on interiors and the links with atmospheres because of this, to answer this question, really. All right, so from this kind of a scheme of the presentation would be, first, I will talk about our solar system giants and what have we learned very briefly. And then I will move towards what we can learn using new information, particularly from JWST, but not exclusively. We will have in the next years also many other missions to observe exoplanets, like Plato and Ariel. So really, we are just starting to understand more and get more data on exoplanets. And then I will tell you how I use all of these to try to understand more about exoplanet interiors. So let's start with the solar system. And this is a nice movie that was made with pictures taken by the Juno mission. Unfortunately, the camera is not working anymore, but before it was taking these beautiful pictures of Jupiter that were really like we've never seen before. We've seen the poles of the planets that we never had pictures before. This camera was, the spacecraft was moving close to 4,000 kilometers in the closest approach to Jupiter, which is very, very close. And also because of those close approaches, we could map very well the gravity field of Jupiter. And this is really the information that I'm using to estimate the interior structure. So here is nicely the pole of Jupiter that we never seen before this spacecraft. So this also opened lots of doors to study the atmospheric dynamics as well of the planet. That is another of the fields that had great advancements thanks to the Juno mission. Now, what I was using was the gravity data. So imagine that we have a Jupiter here. If Jupiter would be perfect, completely perfectly evenly distributed, the mass would be just great, then this could be the trajectory of the spacecraft. We can easily calculate that. Now, in reality, the spacecraft had some perturbations to the perfect trajectory, and we were constantly in communication with the spacecraft, so we knew which was the real trajectory. And all those deviations are really due to inhomogeneities in the mass distribution in the planet. So by mapping the entire gravity fields, we could determine which was the density distribution in the interior of the planet. So this is really what I was doing for the Juno mission. I was doing models of the interior of Jupiter, trying to see which was the best mass distribution, the best density profiles that were fitting the data that we had. So with that, I will give you just this summary of all the things that we learned about Jupiter. So before Juno, just for you to give you some context, we thought that Jupiter was made basically by a core of 100% metals, surrounded by an envelope that was very well mixed and divided in two parts. One part, that was the upper atmosphere here, was made mostly by molecular hydrogen and helium. Then the inner part was made by metallic hydrogen and helium. So hydrogen has a phase transition here. And that's why we move from molecular hydrogen to metallic hydrogen. This phase of metallic hydrogen only happens in the interiors of giant planets. We don't see that in the interiors of stars, for example. So this is one of the very special regimes that we learn about hydrogen just because we wanted to know more about giant planet interiors. Now, something that we learned with the Juno mission is this layer here that we call the dilute core. Basically, what we found out is that in order to explain the gravity data that we were seeing, we needed to have this intermediate layer where basically the core is not separated from the envelope, but is mixed with the hydrogen and helium. And this has lots of consequences for the modeling of the interior, but also the evolution of the planet. This basically means that convection is not so efficient in the interior of the planet. So it's not true that the material is very well mixed, but rather here, there probably is another way of transporting the energy. It means that the planet didn't mix completely. When it was formed, we think that the planets naturally form with these gradients of metals, but then during the evolution, actually the convection slowly is mixing the entire planet. But this didn't happen in Jupiter. So there is some process there that was actually preventing the planet from mixing efficiently. Also, other thing that we learn is this dashed line here, that is actually the differential rotation of the planet. So all the nice bands that we see in Jupiter, actually they don't go all the way to the center. They actually only extend a few thousand kilometers towards the interior of the planet. And this is also something that we learned recently with the Juno mission. And these things really made huge changes on the way that we were understanding the formation and the evolution of giant planets. Now, one other thing that you see here, that this was not something that we discovered with the mission, but actually something that we knew theoretically a long time ago, is that there is a separation between hydrogen and helium. So when you are in the atmosphere, hydrogen and helium are well mixed. But when you go in the interior of the planet, they just don't want to be mixed anymore. There is an immiscibility. They separate from each other. And that's why we have these two distinct layers. So this is something that we knew theoretically from the 70s. But actually, we only got confirmation in the lab a few years ago. So this is also something that was very recently confirmed. And we are starting to learn more about this helium rain, as we call it. So basically, when we have this separation, helium forms droplets. These droplets also trap some other metals, and it rains down because they are heavy. So that's why we have a depletion of helium in this part of the planet and an overabundance in the interior. So there are, as you see, many complexities to the interior of Jupiter. There are other things that I didn't mention, but for example, there might be also some deep radiative zones in the interior of the planet. We also observe with Juno that some alkali metals are depleted very deep into the atmosphere, 100 bars and more. And this depletion of metals could drive low opacities and the appearance of a radiative zone in the interior of the planet that would also complicate the mixing of material from the interior to the atmosphere. So Jupiter is complex. Of course, we have huge and great amount of data. First question we were asking ourselves was like, well, is this dilute core something that we expect in all giants, or is something that we only have in Jupiter? And the answer came only a few years later. In 2021, actually, it was found that this dilute core was also expected in Saturn. And this was using a different method than the one we use. So basically, the way that the interior of Saturn was mapped was using ring seismology. So the giant planets are thought that they oscillate, similar as stars, but due to different mechanisms. And basically, those oscillations are very difficult to see. We've never really seen them. But we can see the propagation of those oscillations in the rings of Saturn. And basically, using that, we could map the interior structure of Saturn as well, and also find a similar dilute core as the ones that we are finding in Jupiter. So this is really telling us that, well, it's not only one exception. The two giants that we have in our solar system have similar interior structures. And of course, then the question is about the others, Uranus, Neptune. They are more complicated. I will leave that from another talk. But we are also now thinking that they might have these compositional gradients and mixing in their interiors as well. So one thing that I want you to take from this is that giant planets are not well mixed. Okay, so there is not that what we observe in the atmosphere is directly telling us about the interior of the planet. And this is, of course, one of the big questions we have for exoplanets, because we like to think, we like to have this picture that, for example, carbon to oxygen ratio that we observe in the atmosphere, that will tell us where the planet was born. But the question is that really true? Is that really representing the entire planet? Or is that only reflecting a very tiny layer? Maybe it's even reflecting inflow of material in the planet, comets that collided with it. So we really need to learn more about all of these to make those connections. And this is really what I want to know more about exoplanets as well. All right. So let me now then move towards the exoplanet part of the presentation. And here, first thing, we have masses and orbital periods of all the exoplanets that we have today, more than 6,000. I lost count. Every time I check, it's a different number. But we have many, many exoplanets discovered in only 30 years. You know, this year is 30 years since the discovery of 51 Peg. So I think it's really amazing what we have done as a community. You can see that all the exoplanets that we are finding are actually quite different from the planets in our solar system. I think it's still quite premature to draw conclusions on this because, of course, we have biases in our measurements. So hopefully in the future, with the Plato mission, actually, very soon, we will be able to fill this part of the parameter space. So I'm very excited to see more results on that. But another thing that you can see is that there are a growing population of cold or warm giant planets that we are finding. Those are very difficult to be found because they have long periods, and then it's more difficult to detect them with transit methods, for example. And also with radial velocities because the signal that they put on the star is also smaller. But we have a growing and growing population, which is also exciting because if we have only the cold giants and the hot Jupiters, we need something in between to understand, to make the links and understand more about how planets form. So I think the key here is that we have very detailed information from our solar system giants, but only for a few objects. We have now a huge amount of data that we are getting from exoplanets. And I think that we really need to put all of that together if we want to understand how planets work better. Now, how is it that we observe exoplanets? So basically, when the planet is passing in front of the star, we can extract a transmission spectrum that is basically the radius of the planet at different wavelengths. And then, depending on which materials are present in your atmosphere, you will change your optical depth, and that will change the radius that you see of your planet. So this is really what we call transmission spectrum. And this spectrum then is the other way around as the typical absorption spectrum. Actually, the bumps that you see there are the representation of the different features, of the different elements that we see in the planets. Now, we have been using, we have been using this technique to observe exoplanet atmospheres for a long time now. So the very first atmosphere that we observed was in 2002. So we were using Hubble, we were using Spitzer to observe those atmospheres. But really advancement in the field came in the last 3 years with JWST. And I will show you why. So first, on the amount of objects that we could observe. So first, before JWST, we only had a bunch of exoplanets for which we had some data. But now, here you can see all these planets are planets that have been or will be observed with JWST with approved cycles, up to cycle 4. So we have many planets, right? It's not just a few. We have a few dozen now of planets that will have data or have already published data. But also, not only the amount of data that we are getting, but also the quality of data changed a lot. So here you see the flux of the planet divided by the flux of the star. So this is a spectrum, different wavelengths. And this is the data that we had for one giant planet using Spitzer. This is same data, Spitzer plus Hubble, and that is with JWST. So you see how really now we are starting to get data that we can actually work with. We can actually tell something about the atmospheric features in these planets. Here is one example of these observations, and this is really, I think, one of the giant planets that we know the best. This is WASP-39b, and it was the very first exoplanet that we observed with James Webb. So we observed it as part of the early science program. And in the community, we were more than 300 people. So this was really open to everyone that wanted to work with the data. We observed the planet with all instruments. Here, I'm not showing MIRI, but we also have MIRI observations. And we made lots of discoveries just with one orbit of James Webb. And we found CO2, that was the very first molecule announced. But I think one of the most amazing ones that we found was actually this bump that you see here, or also here. This is SO2. So it's the first time that we found sulfur in an exoplanet atmosphere, which is also very exciting, right? Because the more chemicals we find, the better we can understand the chemistry and how these atmospheres work. So you can see that we are getting now really amazing information on these giant planets. And that was just one example, right? Now, the question is, how can we use that to learn more about the interiors of exoplanets? That is really the question that I'm more interested in. And first, let me tell you which were the model of exoplanet interiors that we were using so far. And it's basically this one here. So we were assuming that exoplanets have a compact core in the interior separated by an envelope. This envelope was mostly hydrogen, helium, and metals. Everything was well mixed. And then, therefore, when you were observing your atmosphere, then what we were observing in the atmosphere was really representing the entire envelope of the planet, and therefore most of the planet. So this was really the model that we were all using so far for two reasons. First, we didn't know any better, right? We didn't have information of the solar system giants so detailed. We only got that in the last years. We also didn't have better measurements. So the only information that we had was radius and mass. And using masses and radius, there is so much you can say about the interior, right? You need more information if we want to also understand better the interiors of the planets. So that's really why we were using these models. But now really came the change, right? We have more information about our solar system giants that tell us that planets probably don't have this distinct core, but are mixed with the envelope, so they have these gradients that we call dilute cores or diffuse cores. And this complicates things, of course, because then we can no longer say that what we observe here represents the entire envelope. We first need to learn more about these interior structures, more about the extent of these dilute cores, if they are present at all, so which are the conditions for them to be there or for the planet to completely mix. We also don't know if there are other intermediate layers that I didn't write here, but for example, that immiscibility that I mentioned of hydrogen and helium that we know that happens in Jupiter and Saturn. That for sure doesn't happen in hot Jupiters because they are too hot for that to happen. But we don't know about warm giants, the ones that we are finding these days, the ones that we will find with Plato. No one has really studied that before. We also don't know if there are some other radiative zones in the interior of the planet due to depletion of certain metals. We actually don't know very well what is causing this depletion of metals in the interior of Jupiter. It might be some cloud formation that we just don't know very well about. So these are all really open questions. But I really want to know more about this because I think it's really the key to try to use the planets to understand their formation and evolution. So how is it that we are doing this? So we have an interior model. Basically, we model interiors of giant planets the same way as we model interiors of stars. Main difference is that they don't have nuclear reactions in the interior, but they are gravitationally contracting, and that's why that's where they obtain their energy. So planets cool with time. The information that we use, and I will dive more into this in the next slides, but basically we use masses, radius, atmospheric information turn out to be very important because it's our boundary condition. And also we now incorporated that I didn't add it here, but we also have information now on tidal effects between the planets and the stars. And then the information that we obtain is the mass of metals. So basically, that's what we want to know. How is that the metals are distributed in the interior of the planet in the different layers, which are the core masses, which are these dilute core masses, and the bulk metallicity of the exoplanets. So which are really the constraints that we use? How is that we determine which information to use? As I said before, if we only use mass and radius, we have two points of data, then the only thing that we can determine is really the bulk composition in any core mass if it's there. So this simple model is the only thing that we can do if we only have 2 points. But if we have more information, then we can start going into more complex models. So first thing was to actually determine if the information that we are obtaining in the atmospheres is useful at all. So what we did was to model, to use a test planet that was basically Jupiter, but as an exoplanet. And then we knew exactly which was the core mass that the planet had. We knew exactly the mass in each one of the layers. And we tried to use our code to see if we could retrieve those parameters or not. So then when we are using only radius and mass, and we were trying to retrieve the core mass, as you can see, we could not say anything about the planet because, again, we had very little information. So then next, we tried using atmospheric data as well. And it turned out that the atmospheric metallicity, even though it's not the same as in all the other layers, it puts an upper boundary and is very useful to constrain interior properties of the planet, such as the mass of the core, for example. So this was really one of the first tests that we did. And then we learned that definitely having those spectra and information, mostly on the metallicities in the atmosphere, helps to constrain interior properties of exoplanets. The other piece of information, and I think that is really, really the most useful one, comes from tidal effects. So some of these giant planets are not really like this, but they look more like that. They are deformed due to tidal effects. This doesn't happen to all of them, of course. They need to have, for example, an eccentric orbit or some other giant that is also perturbing them. But in the case where these tidal effects happen and the planet is deformed, then if we measure that deformation, that is directly telling us, again, similarly as we do with the gravity on the solar system giants, that deformation can tell us directly about the density distribution in the interior of the planet. So those are called log numbers. So if we can measure those, then we will get some information about the interiors of the planets as well. And basically, the way that you can measure this is if you have a perfectly spherical planet, then when you are observing the planet going all around the star, you will have a certain light curve. But if the planet is not spherical but is deformed, then the geometry is different, and then you actually see a different effect in the light curve due to this deformation. And basically, we just couldn't measure this very well before. We have it for 5 planets, this love number. But now with JWST, actually, we can get this with a very good accuracy. So there are now a few programs that were accepted to actually observe and detect this with JWST. And actually, we also did studies with some of my team members about using this technique for Plato and Ariel. And we will get great data with both of them. So now we are trying to find which are good candidates of these and for which planets we can measure these. But this is, I think, really promising because love numbers, as I will show you now, are really, really good at telling us about the distribution of density in the interior. So here, what we did was to add the love numbers to our interior calculations and see if that was helping us to retrieve the interior properties of the planet. And you see here for the bulk metallicity and the mass of the core, particularly the mass of the core, is really, really improving when we have both the atmospheric metallicity and the love number. So the error bars are also very tiny. We also found that you need to have a good accuracy of these measurements, so better than 40%, in order to actually being able to say something. So if you have a love number, but the error bar is huge, it's not really giving you much information. That's why we also need to do this with this next generation of instrumentation. We have used, though, this information for the 5 planets that we have it. And this is the results that we found. So these are the 5 planets for which we have love numbers measured. And this one actually is one of the best ones that we have, and HAT-B 13b is also, these 2 are the best ones. These ones have huge error bars, so that's also why our results have huge error bars as well. So here you see the retrieved core masses of the planets, assuming different atmospheric metallicities, that this is also something that we need to improve for all these planets with new JWST results. For example, this one, HAT-B 13b, for this planet, we have a very good love number measured because it's a special configuration with another giant. So then measuring the precession of the orbit, we could obtain the love number. So it's a special case. But we don't have good atmospheric metallicities observed. So hopefully, we will get those next year. And then we will also shrink this error bar. And then you can see that this one, number 4, number 5, they have very, very large error bars. We also retrieve parameters for these different kind of structures of the planets. So here you have the metallicity in the dilute core region and the mass in this dilute core region. And you also see that we can get those with large error bars for all these planets. But I think that this is just the beginning, because once we get better and better information with the new instrumentation, we will be able to actually map the interiors of the planets much better. And of course, learn more about all of these structures that are really key to move forward and understand the links with planet formation as well. So my take-home messages, first about what we learned on Jupiter and Saturn. These planets are not homogeneous. I want you to, if you take that from the presentation, that would be great. That's accomplished. Their structures are, of course, much more complicated, but we have much better data, right? We could go there, we can make measurements. For Jupiter, we even have in situ measurements of the atmosphere. So that's why we also can map their interiors with much more detail. But for exoplanets, this is really the starting of this field. Before, we just didn't have good enough information to actually know them better. But now, with the new measurements that we have and the better knowledge on how giant planets work, this will really start the field of exoplanet interiors. So I will leave there with the collaborators in the work that I showed, and I hope you have many questions. Thank you.
Thank you, Yamila, for a wonderful talk. I'm pretty sure there will be lots of questions.
That was a really nice talk. Do we see any exoplanets with rings, and could we use those to do the same kind of internal science that we do with Saturn?
I don't think we have any confirmed detection of rings. People is trying to find exomoons. There are a few candidates, but again, nothing really confirmed on that. One of the two, either, well, one of the two, either rings, but mostly moons, I think, would help with this love number calculation. But we don't have any detected so far.
Wouldn't the rings be more obvious than the moon?
The thing is that you need to see the interaction between two bodies to get this love number, and with the rings it's more difficult if you cannot define them.
Okay, thank you.
Yeah. Thanks for this wonderful talk. It was really interesting. So I work on the interior structure and evolution of stars and not planets, and I'm just trying to see what we can learn from these studies also for stars. So I find it's really exciting that you find that convection is not super efficient in the interiors of planets. Is this process specific to these planets because of the change in opacities, or is this something that could potentially be applied to stars as well?
There are two different things. If you go very deep in the interior, you have this dilute core, and basically there you have a very steep compositional gradient, and that is what is inhibited your convection. But if you go higher up, then what happens is this opacity effect, and that is what is causing the radiation there. So there are two different effects in different places. Yeah.
Cool. And what about the differential rotation? Because this is, I think, a general problem for structures of any stellar object, that we don't have very strong constraints on that yet. Do you think we can learn from planets as well to inform a differential rotation in stars?
So basically the way that we map the differential rotation is we use the odd gravity harmonics. And the odd harmonics, so the even J2, J4, those are giving you global information. But the odd harmonics work if you don't have hemispherical symmetry in the planet. So the fact that we were measuring the odd harmonics was telling us that there were differences in the northern and southern hemisphere that were directly linked with the weather. So all the perturbations in the gravity were due to the differential rotation, basically. So then we could map how deep those perturbations extended. But for that, you need a probe. So I don't think you can do the same for stars. But if we learn why this differential rotation stops, and this is really something that we are trying to understand, maybe that will help out. So there are some ideas. We think there is a sudden drop in the conductivity where this differential rotation drops. So maybe magnetic drag is playing a role. And if we learn more about that process, maybe it could be useful, but I don't really know. I don't know enough about stars to actually know if it could be useful or not.
Okay, nice. I think we should discuss this more later. Thank you.
More questions? Yes.
Thanks, Yamila. I always like your performances, as you know. I have a bit more technical question, maybe, because what you call retriever, we tend to call it inverse modeling of stellar structure, or forward modeling. Can you? And we are a bit. It's easy, by the way, to measure differential rotation. Not easy, but we can do that from waves.
Okay.
We don't need a probe to go there, luckily. But are you hitting degenerates also when you do your modeling, and do you do it in a forward or in an inverse way? Can you say a bit about that?
We do forward models, but then we run thousands of them to obtain the retrieval. Yeah. But it's more a forward model, really, that we are doing. Yeah.
And so you're hitting degeneracies?
We have degeneracies. Yes, that's why I'm desperately trying new observables that we could put in the picture to break those.
Any more questions? Hans.
Thanks for the nice talk. I have a question with respect to one of the things that you mentioned, was that you retrieve the love number of Saturn, I suppose, with the dynamics of the rings.
The interior structure. Yeah.
Yes, and how does that work?
It's
So-
basically similar to what you guys do with the stars. So there are oscillations in the planet, and you can map those oscillations to what happens in the interior structure using waves. Similar as you do with
No,
the
but
stars.
the rings.
Yeah, on the rings. So what we see is the waves, how they project on the rings. That is really what we are measuring.
And is that easier than on the surface of the planet itself?
We haven't really seen it on the surface, so we don't know if it's why, really. So there are a few instruments that have been built to actually try to see these on the planets themselves, but with no luck so far. And there are some few tentative detections, but apparently it's not so easy.
So that those waves propagate into the ring system of Saturn then?
Yeah.
Ah, yeah, it's interesting. I didn't know. Thank you.
Sorry, just a quick follow-up on this. So can you extend this to exoplanets? What you can do for Saturn's rings, if you could directly image?
Tried. I tried to estimate which will be oscillations on planets, but the thing is that we are not entirely sure of what is causing them in the giants. We think that it's basically huge storms. And then it's difficult to kind of predict something that you don't know what is it. I made some tentative models some time ago, but they are such tiny oscillations that so far with what we have is difficult to measure. Yeah.
Yeah, Emma.
Thank you for the nice talk. My question would be about the perturbations to Juno's orbit. So you have the calculated one, and then you calculated the internal structure with the perturbations. My question is, couldn't this be also influenced by Jupiter's moons? Basically?
Yes. It's definitely influenced. So in the model, we put everything. You put the moons, you put so Io is losing material. There has this sodium torus, and there is a radiation torus that forms around Jupiter. We have to also put that. You have to even put the weather of the Earth when we are receiving the signal. So those are very, very complex calculations that I was not doing. They were just giving me the numbers, and then I was using that for the interior structure. But actually extracting all of these from the signal is very, very hard, yeah.
Super cool, thank you.
Yeah.
Thank you again for the very nice talk. I was a bit curious when you mentioned in the beginning of your presentation for Jupiter the presence of metallic hydrogen, I believe. And you also mentioned that it's not formed in the interior of stars. And I was wondering, first of all, what it is, and secondly, why it can be formed.
Yeah, I don't have any plot, but if you see the phase diagram of hydrogen, this metallic region happens only in a region when the temperatures are not as high as in the interiors of stars. So it's a cooler region of the phase diagram, let's say. And that's why it doesn't happen in the interiors of stars. So it's a very small region in the phase diagram of hydrogen that only affects our giant planets. And what is it is also difficult to answer because we have very few lab measurements. Basically, the only thing that they measured is that how the conductivity of hydrogen changes when they pass this threshold. And then we know that it behaves as a metallic fluid, but that's all I can really say about it.
Thank you, very cool.
More questions? Yanis?
Thanks a lot, Yamila. So I still remember the frustration soon after commissioning. We got the first ERS data and guarantee time observations, also with MIRI, with a medium resolution spectrometer. And then the first thing people did was to degrade the data, the resolution. They immediately dropped it from 3,000 down to 100 or 200, because that was the only way to get some, spectral retrieval working. Now I'm talking about, 4 years ago, and I was just very curious. From your perspective, has there been development in trying to fit higher resolution data from Webb? We cover 4.9 to, afterwards you have the clouds and whatever. But I was just curious what the status there was, just because of this frustration. I remember a lot of people being frustrated that the models, you had degeneracies
Immediately,
and all that.
everyone tried to go back to what we had before, right?
Yes,
because the tools were working then.
Precisely. So,
yes.
Yeah. I'm just curious what the status is, if there's...
Yeah, there were many developments. So there is a huge part of the community that is trying to improve that, also using machine learning, all kind of, whatever we can get to use, we use. I'm not really doing those retrieval calculations, but they definitely improve, and they are also working more together with the high resolution from the ground. We have very high resolution spectrum, and they are also trying to retrieve those and get better tools for the ELTs. So now I think those communities are talking more to each other, and that also is helping. Yeah, but it's a problem. We also have the generacies there.
Yeah, indeed.
Yeah.
I mean, especially with some other instruments in the future as well. Coming up,
and if you go to smaller planets, it's a whole mess.
No, but that's good then. All right, thank you.
Questions? Frank first.
Hi, Yamila. Very nice talk, thank you. I was wondering also about basically the orbit of Juno and the deviations that you get from the density variations. How large are those deviations? Like, is this less than percentage? Very small?
Know.
It's like, how significant are these?
No, to be honest, I don't remember those.
Okay.
No, if I tell you a number, I would be lying. I can check. I
That's
I
all right.
have it. I have
No,
it. I
that's
just
all right.
don't remember.
I was just curious because it feels like it would be so small.
We can measure really small deviations, like the previous gravity data that we had before Juno, the error bars were 2 orders of magnitude larger than what we got now. So definitely it's much better, but I don't remember exactly. Yeah.
Yeah, if I may ask another question. I was wondering if you can really model the interiors of planets in isolation, like ignoring the star, or if you also need to take into account effects from the star, like irradiation, and how important this is in your modeling?
Yeah, it's very important. So I didn't even enter there, but the closer you are to the star, the more the irradiation affects your interiors. It's not really the case for the giants in the solar system, that their energy flux is dominated by the interior. But the exoplanets, the hot Jupiters, the irradiation, basically what it does is the inflation that we see is not an inflation, is that the irradiation prevents the planets from cooling. So basically, during the evolution, the planets contract and cool, and if you are injecting extra energy, you prevent that cooling and that contraction, so the planets remain inflated. And that is what we see in exoplanets, and we need to take that effect into account, that we also don't know how the energy is propagated in the interior, where is deposited, and all of that also affects the modeling, yeah.
Interesting, thanks.
Catherine. Yeah.
Thank you for the nice talk. I was wondering about the gravity data. Do you, at that level, is there a possibility of seeing dynamical effects in there, in the sense of, well, if you have pulsations, for example, in Jupiter, would you be able to see that in the gravity data, or are we not sensitive enough for that?
There is one paper trying to see the change of those with time, but I think it's so tiny that I'm not entirely sure that we can extract any information from it. Yeah. Maybe if we had much longer observations, but so far with the data that we have, it's not huge.
Hi, Yamila. Thank you for the wonderful talk. Also about the gravity data. So you see these deviations from the orbit, and then it has to do with the moons, but also with the planet itself and with the weather patterns, I guess, on the planet.
Yes.
How stable are these? Do you know something from this, from multiple orbits?
Yes, so we mapped the planet in the, so we did many different orbits all around the planet. So the idea was to do a complete map. And definitely you can see the weather, the great red spot and other storms definitely have a signal. It's mostly, there are certain belts that have more influence than others. So we also studied that, which is really the ones that are causing the largest perturbations to the signal, and is one of the belts in the northern hemisphere is particularly strong in the perturbations. But we are trying to understand all of that now.
Okay.
Yeah.
And would it be because it's denser, or what, this particular belt?
I think it's just somehow thicker than the others, but then trying to understand why the belts are not completely symmetric is another whole area of dynamics that is also very interesting. But we are starting to understand more about it recently. Yeah.
Great. Thanks a lot. Wonderful.
I think it was Connie after.
One more, if I may. One of the great motivations for us building Plato is that actually you do seismology of the star and exoplanet studies together, and that gives you a 10% is our aim, accurate age. You haven't said anything about how that could help you to understand your formation models. Can you comment on that?
A lot, actually. I'm very excited about that from Plato. That particular point is very exciting because now the error bars that we have for the ages, as you know very well, are very large. And then it's very difficult to model the whole evolution of the planet. And that's one of the reasons why I'm not doing evolution models. I'm doing static models. I'm just saying, okay, the planet right now is like this. I'm agnostic on where it was formed and how it evolved. But once we have ages, then we can do evolution models, and that will even more improve our interior constraints. So yes, definitely, I'm very excited about that as well.
Peter.
You just mentioned that some of the belts may have a different thickness, so I guess you mean inside, but are there also in those missions observations of the very surface of the planet, like grazing observations of stars further there to see the very top layer of the atmosphere? And sub-question with respect to the belts, do you see also a structure extending outside? Or
yeah, so Juno has a microwave radiometer, and it has different channels, and each channel is looking at different wavelengths, so we can see deeper into the atmosphere and make more detailed maps of the distribution of elements in the interior. And that's how we detected this depletion of the alkalis, for example, using that instrument. So that's one of the things. We are also doing now, and actually we haven't published it yet, but it's coming soon, occultations using the Juno. And that also is helping us to map, but it's very higher up in the atmosphere, low pressures. Yeah.
Any final questions?
Yeah, this is one about the images that you showed of Jupiter. They're incredibly beautiful. And how were they made? Because if you look at the colors, and we know that colors are made using different filters. How is this done here? And is this really, this is it's incredible.
The Juno Cam, that unfortunately is not working anymore, but it was first developed more as an outreach instrument. So it was not in the original plan of the mission. Of course, it was the first thing that NASA told the team, like, you need to have a camera. And then they added it. And it was basically all the raw images were released in the website, and the people were taking them, playing with Photoshop and uploading them. And what I showed is a result of that. It's basically someone playing with Photoshop and putting the images together, creating a time lapse.
Yeah.
But it's not any, it doesn't have any meaning. It's just enhancing the contrast.
Yeah. Okay, thank you.
Maybe I can ask one final question. So generally, if you look at a lot of proposals for grants or for even JWST, you see people make the connection between carbon to oxygen ratio and plant formation, which largely is a reference to very well-known study by Karin Neuberg in 2011. So what do you think after all these JWST observations the consensus is, and where should the field look at in terms of connecting plant formation to plant atmospheres?
I think that, so I think Karen's paper was great actually, because it started all this field to trying to understand those links better, and in that sense it was a very motivating paper, but of course it's a very simplified vision, and we know that now, not only from the planets themselves, but also from the formation and the disks and how they evolve with time. So, but it really triggered a lot of research on that area, and in that sense I think it was great. But now we know that we need to make better estimations. We need to understand these things better before we can say something. Some problem that we have for Jupiter, for example, is that we cannot really match very well some of the metallicities that we observe in the atmosphere with the interior. And we think the planet was enriched with time, with comets and impacts. And if that is happening in exoplanets as well, then there is a disconnect with the interior and the evolution as well. So there are lots of things that we still need to learn to actually being able to map, to make that map so directly. Yeah.
Okay, before we thank Jamila, just an announcement. So she is here until tomorrow 2 p.m. and her schedule is on Slack. So please feel free to go and add your name if you want to do a one-on-one meeting. There will be also, she will also join GATKIP in the second half after Rose's discussion, and some of people led by Miriam will go for lunch in Alma with Jamila. So it will be also a nice walk. So yeah, feel free to join tomorrow. And there are still a few spots left for tonight's dinner in the city center. So again, go to the spreadsheet and add your names there.
And thanks for all your questions. This was great. Yeah.
Okay, let's thank Jamila again.